day of conferences. It is my pleasure to introduce the talk of Mr. Alexander Gnedin from the Queen Mary University in London. He's going to talk about a new random graph growth model. So,
thank you for introduction. Thank you, organizers, for this wonderful opportunity to speak here. So this is a joint work with Michael Farber and Vejit Manan, the topologists, and the idea of constructing actually more rich structures than the graph is due to Michael Farber. So the idea is fairly simple: to construct graph by a certain sampling process, and probably it's best to just put it on the picture. So we start a graph with nothing and add with complete graph, passing through certain stages by just sampling. And the sampling goes as follows. We have a pool of virtual elements, and at start the pool has virtual vertices of the graph. Suppose we have them 5, and we sample. So what can we sample? We can sample only a vertex. We put it here. We can call it vertex 1. Okay, then we keep it sampling, sample. So this is removed. It's no longer virtual. It becomes occupied, from virtual to occupied. Okay, we sample another vertex here, say this. Okay, we'll put it here. And this vertex becomes occupied. Now, potentially, it's possible to draw an edge here. And we put this edge as a virtual element in the pool. So we have now an edge, 1, 2. And keep on sampling. But now we can sample both edge and we can sample edge, or we can sample a vertex. Suppose we sample, okay, of course, it's more likely to sample a vertex in this situation. So we sample vertex 3. Okay, vertex 3 here. But now there are 2 more potential elements, and this is 1, 3, and 2, 3, which come here. Okay, now we sample, and we have now a lot of vertices. Suppose we sample 1, 3. Okay, we remove it from the pool and put it here, and so on. Okay, so on each stage we get a graph and call this graph Gn. Starting from n virtual vertices, each subsequent state is a graph with some number little n of occupied vertices. They're connected by some number k of occupied edges. And at that state, the pool contains complementary set of vertices, big N minus little n of virtual vertices, and complementary number of virtual edges, which could have been added to already existing graph. So the graph is simple. Everything is simple. But of course, we can consider edges as oriented from bigger label to small, but that doesn't really matter. Okay, so is this a clear picture? Good. Yeah, sure.
When do 2 points qualify to be chosen as an edge? I have not quite understood. When do you choose it?
This is just labels of an edge. It has no these points. It's just edge without points. You just put it. It's 1, 2, you put it where it belongs.
But I think the answer to this question is that as soon as you add a vertex to the graph,
yeah,
all new
potential edges are put in the pool. All potential edges are put in the pool. That's the point. That's how it works. Okay, so there are many questions can be asked, questions about the graphs. But the first most obvious is what is the number of edges at time when the number of vertices becomes little n. Okay, and that's the random variable which we will discuss in this talk, and I call it xn. This is the number of edges in Gn. Say if we add here element 4, then this is a separate thing. So G4 will have this isolated. Okay, but at this time, if we edit the last vertex, we put 3 edges in the pool. Okay, so let xn be the number of edges, and nice thing about this xn, it's an increasing Markov chain, and because it's Markov chain, we can say something useful about how it grows. Of course, we can represent this thing as a Earn model. And to make this the Earn model, just call an edge black ball and a vertex white ball. Then, in terms of this Earn model, the edge counting can be represented. So a state of the Earn is some number of white, some number of black balls, and you put them in a row. So, okay, so when you sample, say, an edge, you can put here a black ball, and when you sample an edge, you can put here a black ball, and when you sample vertex, you put here white ball. So, in terms of this string, the edge counting can be represented, and the Earn works as follows. If you have here a black ball, you put it in the row, and if you draw a white ball, it is replaced by some number of black balls. So the number of white balls will be smaller, smaller, smaller from n to 0, and the number of black balls will be variable. It's some Markov chain, this xn. Okay. On the other hand, you can represent this as a sort of insertion algorithm to construct thing using a slightly different principle. It is the following. So you start, say, this example is with n equals 5. You start with 5 white bits in a row, and you scan the string left to right and update the string. So you look at the first bit, it's white, okay, and you can nothing to add. Then you look at the second, and when you look at the second, you take a black bit and insert it in the string to the right. Okay, so at stage, say 3, we could have this situation. So the first was scanned, and nothing was added to the right. The second was scanned. We are, say, at second position. Then one black comes to the right of this second white position. Then we are at state where we are at the third white bit. And at this moment, 2 other black are added to the right randomly. Just insert in the string. Okay. Now, what is xn in this situation? So xn just counts the number of runs of black substrings between the white bits. Okay. So at this stage, suppose we are at this stage, then the number, say this would be time 1, 2, 3, 4. Okay, suppose we are here. At this time 4, xn is equal to 1. It's the number of black to the right, to the left of n's white. Okay, so the last white would be 5th in this row. This is 5th, and xn. So this would correspond to the graph G5, and G5 would have then 1, 2, 3, 4, 5 edges. Okay, and after that, the only edges remaining, which are edited to make the graph complete. Okay, so at time G5, not all edges are present. There's still some left, but there are no more vertices there. Okay, so this is the insertion process, and it's very useful because there is obvious exchangeability in this process, which can be used to do all calculations. Okay, now following Jim's tradition, I will do a summary of results. If you look at this string of white and black beads and look for some limit shape of the string as n goes to infinity, then it can be divided in 3 phases. The initial phase, you have only vertices, and you keep drawing vertices, and the number of edges is too small to get drawn. So at the first stage, you will have only vertices added to the graph and very rare edges. So at this initial state, the scaling should be cubic root of n. And on this scale, the appearance of black spots will be according to certain non-homogeneous Poisson process, which I will describe later. Okay, then in the bulk of the process, when the number of vertices becomes of the order of the full graph, something like, say, big N divided by 2 or something like that, then the edges will appear linearly, meaning that between two vertices, you will insert some linear number of some or big O n number of edges. Okay, so this runs of black beads will be linear in n. And this is most interesting, of course, part of the process, which leads to certain shape for the process approximating the number of vertices, and the fluctuations about this deterministic shape will follow certain Gaussian diffusion, which I will describe later. Now, in the last stage, we have very few vertices left and a big number of edges. And at this stage, the runs between the number of inserted edges between two vertices will be of the order of n log n. And with this scaling, the last vertices will appear according to now homogeneous Poisson process with this scaling. So the whole picture is the following. A start is Poisson, non-homogeneous Poisson, then the bulk is Gaussian in terms of fluctuations, and the end is Poisson again. Okay. Okay, now let's look in the details, for which we have still some time. Okay, because it's a Markov chain, it can be described in terms of transition probabilities, and transition probabilities follow so-called negative hypergeometric distribution. This is a number. Suppose you have an urn with some number of black and white balls, and you sample without replacement until you get one white. How many draws you need for that? Well, this distribution is called negative hypergeometric. Okay. And so this transition probability follows negative hypergeometric distribution. With this notation, we can compute expected increment, expected increase. Of course, the number of edges will be increasing, and the expected increase is given by this formula, and the expected variance, and the conditional variance is given by that. So given the graph Gn has k edges, the increment in terms of the number of edges is given by these formulas. The moments are given by these formulas. Okay, so we have recursion. We have some formulas. I can see what happens with the moments. For the moments, we have this recursion for the mean and this recursion for the variance. They do not look very terrible, and the first can be safely solved, giving this combinatorial formula, and the second can be solved in terms of the first. So to compute the variance, you need to know the mean, and the mean enters this recursion. Okay, so finally, we have some formulas and can think about approximation, what happens when little n becomes big and big N becomes big. So the analog of the first recursion for the mean is just this linear differential equation. It looks harmless, however, it has singularity at 1, and that brings a lot of trouble when studying asymptotics. This 1 minus t is the last time. So after certain time scaling, the time runs from 0 to 1, and the mean number is described by this differential equation, which has easy solution with notation that big L is logarithm of 1 minus t. So it's just this expression. And if you view this solution to differential equation as approximation to the mean number of vertices, then the quality of approximation is 1 over n uniformly everywhere, with except the last piece. The last piece is always a trouble, so scaling the whole time from 0 to 1, you have everything smooth and nice away from 1, but near 1 there is some, this singularity makes some trouble. In particular, the quality of approximation will deteriorate when you approach the end of the process. Okay, so with scaling 2 over n squared, mean number of vertices in the graph minus this limiting function, we will get this error. Similar thing can be done with the variance, and in continuous counterpart of the recursion for the variance, this differential equation, it's again linear, and this non-homogeneous part involves the function which appears by computing the mean, and this can also be solved explicitly. Okay, so this is explicit solution. And recall that L is log, so okay, to recall the notation, L is logarithm 1 minus t, and the quality of approximation to the limit is again 1 over n with suitable scaling away from the singularity at 1. Good. Okay, so to summarize the previous slide, we have two limit shapes. One limit shape is for the mean, this function of this kind, yeah, going to infinity at 1. And the shape for the variance, for the curve approximating variance, it is this. But note that the scales here are different. This is from 0 to 1 scale, and this is scale from 0 to 0.10. So this has certain maximum, then goes to 0, and this goes to infinity. I mean, goes to infinity. So mu n behaves like that, and the variance of the number of edges behaves like that. Well, with this in hand, it's not hard to prove the limit shape theorem, which says that in probability, the number of vertices scaled this way will converge to this limit shape. So this will be with suitable scaling, the number, sorry, not the number of vertices, number of edges. The number of edges will grow according to this curve. Okay, so now next question. Okay, we have some limit shape. What happens if we look on the microscope? If we explore the fluctuations. Okay, but before going to that, let's look what happens at the begin of the process. And at the begin of the process, we have a Poisson approximation on the scale cubic root of n. That is to say, when we sample from this pool of virtual elements, the first edge will appear after cubic root n time, approximately. So we need to sample n to 1/3 to get the first edge in the picture. Before that, we will have only vertices, vertices, and vertices. And moreover, the time of this will be sort of exponential, but it will not be exactly exponential. It will be cubic root of exponential variable with with parameter 6. So the whole process in the early stages will be Poisson process of appearance of edges, and this Poisson process will have this quadratic intensity t² over 2. So the first point of this Poisson process with this intensity is precisely this random variable whose cube is exponential variable. So this cubic root of exponential variable. Okay, that's the first stage. Okay. Now let's look in the bulk. In the bulk, you can perceive that there is some central limit theorem, and in a simple version of this theorem, you just subtract the mean number of edges at time tn. So little t is now time parameter, say 1/2. Little t is 1/2, and big T is the size of the whole graph. So in the middle of the process, you have x 1/2 here, sort of you subtract the mean, you divide by the variance, and this will converge to normal distribution. That can be perceived. That's not obvious, of course, but that can be perceived. Moreover, you can seek for a functional limit for that. Let's subtract the mean and scale by square root of the variance. Not exactly by square root of the variance, but by n to the 3/2. So the variance will grow like cubic root. And so let's just divide by this and look what happens with this process in the limit. So just subtract center the process and scale by some power of n, and look what happens. Okay, so what happens is the following. Let's call this process scaled number. Let's call this scaled number of vertices yn. For each n, we have some piecewise continuous process, and look what happens in the limit. Okay, and then it turns that this scaled number of edges, scaled and centered, will converge to certain diffusion process, which can be described as a Gaussian bridge with this explicit covariance function. Psi comes as the limit variance. Okay, so this is covariance. And alternatively, this limit process can be described as stochastic integrals, where B is the Brownian motion. So it looks something like an Ornstein-Uhlenbeck process, but it's not a Ornstein-Uhlenbeck. It has the features of a bridge because this process starts at 0 and it ends at 0, and it's Gaussian. So alternatively, you can describe this process as a unique strong solution of this stochastic differential equation. Okay, so if we would have here just one, so this term and this term would be one diffusion. If the diffusion term would be one, that would be just explicitly the Brownian bridge. But it's not a Brownian bridge, it's something different. Okay. So that's the limit process, which appears by suitable scaling the number of edges. And with a few minutes left, I will explain how this result has been proved. So we look at the number of edges xn is a Markov chain, and Markov chain has some generator. Let's write down this generator and try to approximate this generator when our parameter big N, number of vertices, goes to infinity. So with some manipulations, it can be seen that the generator is given by this formula. So this will be this operator, and it can be shown using some technique from Markov processes that showing convergence in functional sense to some limit is possible by showing convergence of generators on sufficiently rich class of functions. Okay, this has been done, and this allowed us to show convergence, functional convergence of the scaled number of edges to the limit process, however, away from one, because at one, the generator and everything is a singularity. The standard technique doesn't work here. So if you look in the book of, say, Etienne Kurtz or Kolokholtsov, then there is nothing about the situation where the operator generator has some singularity. So it's not Lipschitz and near one. So this brings us some trouble. So we need some special ideas to show full convergence on the full interval from 0 to 1, not just away from 1, but on compact. And this has been done using yet another idea. It can be shown that, so xn is the number of edges. If you center, subtract the mean, and divide by this thing, then wonderfully, it turns out this thing is a martingale. And because it's a martingale, can take a square of its martingale. And you take a square of martingale, get a sub-martingale. And for this thing, you can apply one classic inequality due to Cho to show that the fluctuations near 1 can still be bounded in some way. And with these bounding fluctuations of the process near 1, we could show that the whole family of processes xn is tight, so the measure doesn't go to infinity. So Prokhorov theorem can be applied here. we have convergence of finite dimensional distributions using the technique of generators, and we have tightness using technique of generators and using this special idea of restricting fluctuations near one. So we have full convergence on the compact interval from 0 to 1. Okay, so last 5 minutes, last stages. What happens on the last stages? On the last stages, we have again Poisson approximation, but now Poisson approximation for the process of sampling of vertices. Now we have, at the last stages, we have a lot of edges, but very, very rare vertices. And to deal with this, we'll look backwards. So we'll look at this string of white and black bits in the inverse time, and it can be shown that this in inverse time, these white bits appear according to Poisson process, meaning we have shown that these gaps have exponential distribution. By scaling with n log n, we get some point process which is converging to Poisson. Good, that's actually the whole thing. And now I wish to finish actually with a problem which Michael Farber posed. And the problem is not constructing a graph, but the problem is to construct a random simplicial complex. So as said, Michael Farber is topologist, and when he's speaking about something random, he means every time something uniformly random. So suppose you wish to construct a simplicial complex on 1 to n, and it is a system, combinatorially, it's a system of subsets closed under the operation of taking a subset. So let's have a certain pool of first vertices. Okay, you take a point here, you take another point. After you have 2 points, you can put here an edge. After you have here 2 edges, you have a triangle, and triangle potentially has a face. So you can put here a face. And keep on adding virtual elements to the pool and keep on sampling, constructing bigger and bigger simplicial complexes. The question, what sort of structure appears here? The answer is, we do not know how it behaves because there is a big problem here. The number of points and edges as a couple is a Markov chain, but the number of points, edges, and triangles is no longer a Markov chain. So, and we do not know how. It is possible to estimate number of triangles in this graph, but it's very difficult to understand how it behaves like a random process. Good that my talk is finished. Thank you very much for